Hello, everyone. Thank you for having me here today. I'm Rivka Fidel, as Chris said, and I'm very excited to talk to you about biochar as a potential solution for mining pollution. So, why exactly do we need a new solution? What's wrong with what we've got exactly? Well, there's a lot of challenges that I'm sure some of you have heard about with mining pollution and specifically in the desert. So, firstly, the most common approach to mine reclamation is basically cover it with plants. So, the challenge with that is like we want to increase plant cover, and this will reduce the spread of contaminated dust. But the soil, I like to say that the soil feeds the plants, and the plants feed the soil. And this means you need healthy plants to restore the soil, and you need healthy soil to restore the plants. So it's kind of like chicken or egg, and um, when you don't have one, you don't have the other, and it's hard to get started. So to kind of jumpstart things, you need to add some things to the soil to neutralize the acids, immobilize contaminants, and then in the desert, we have to add water and add something to the soil that will help retain water. So compost is very common to do that, as well as fertilizers and liming agents. But if you just apply those once, you can't just set it and forget it. You may have to keep applying because they don't stay in the soil. So if the plants aren't happy with that one application, you have to go back and spend more money applying more fertilizer and more liming agents like calcite from ground up limestone to increase the fertility of that soil, whereas biochar only needs to be added once. So there's lots of details that I will get into, but that's the basic challenge. So what is this biochar stuff? Well, I like to say what are biochars, plural, because biochars are a diverse suite of man-made pyrolyzed or charred, same thing, organic materials intended for soil application. And they can be made from a lot of materials. By organic, I mean just coming from something recently living. So this can be any kind of plant material like tree prunings or corn cobs. It can also come from animals like bones. We have some more plant materials, bamboo, wood waste, leftover, any part of the plant that you're not using, agricultural waste, those are ideal because they're inexpensive. And also, you're not taking up space on the land to grow stuff to make biochar. And yes, there's manure also. So, what is this pyrolysis process that we use to make the biochar? Um, so I like to call it the dark side of fire because fire has two steps. Um, we call it combustion, and the first step is pyrolysis. The second step is oxidation. So pyrolysis occurs when you have some kind of solid fuel and you raise the temperature a lot, like higher than 300 degrees Celsius, usually between 300 to 800 or 900 degrees Celsius. And then you heat that up under low oxygen conditions. So you're baking it with no oxygen, essentially, very, very hot. And this results in the formation of gases and oils and char. And these are all, very flammable. Is the sound okay? We're okay? Yeah.
Yes.
Okay. Thank you. All right. So those are all very flammable. And if you were to add oxygen to this system, then you would get the second step of fire. And you would end up with just carbon dioxide and water. And that carbon dioxide would go back into the atmosphere. Not ideal. So what happens if you just make the char? I don't not going into depth on this one, but there's climate benefits of making the char and not having this second step because plants take up carbon dioxide, and then if you make the char, you're locking the carbon away in the plants, in the biochar that the plants took up, and So what this pyrolysis process looks like, well, it actually happens every time you burn a solid fuel, because you don't have complete combustion right away. Instead, any part of that fuel that's charring is undergoing pyrolysis. Um, so you end up the solid fuel doesn't mix easily with the atmosphere. The gases can't penetrate into it. So you get this low oxygen zone closest to the fuel. And that's where we find some of these flammable gases just kind of hanging out. And then further away, the oxygen can come in and mix with the flammable gases, um, and react with that second step of combustion, the oxidation process, and then you end up with your combustion products up top. So that's what fire is made out of. Whereas fire is light, whereas produces light as a byproduct, whereas pyrolysis is dark, hence the dark side of fire thing. um, so a little so that chemically these things are very different, the starting and ending products. So you start with a biomass that has yes, lots of chemicals, but these are all very tasty looking to microbes, so they would normally gobble those up. Whereas after pyrolysis, you get biochar, which the microbes don't eat so much. It looks like kind of like a honeycomb. All these hexagons that are bonded to each other are very, very strong. The microbes can't eat it. If you use specific pyrolysis processes, you also get bio oil, which can be turned into a drop-in fuel similar to gasoline. And then again, if you modify the pyrolysis process a little differently, you can also get syngas, which will burn like natural gas. So the just quick overview of the types of the ways that you can produce biochar. There's slow pyrolysis, takes hours to days. Fast pyrolysis happens in less than 1 second. Autothermal pyrolysis, which is a new type invented at Iowa State University, where I got my PhD. Also, fast pyrolysis was invented there. That is a case where you let in just enough oxygen to create some heat for you, so that you're not like burning something else to make the heat, and so it self heats. So autothermal self heating, and then gasification has been around along with slow pyrolysis for hundreds of years, maybe not that many hundreds for gasification, but this is where you add just enough oxygen to produce an optimal amount of those flammable gases. So you might have heard about gasification of coal during World War II. In Germany, that's what they were doing. They were using coal instead of fresh biomass, and so they weren't making biochar or anything like that. And then you might have heard of this other term. You might encounter, if you Google biochar, you might also encounter torrefaction. That's just making toast, just heat it up, dry it down. That can be used before pyrolysis if desired to dry out your feedstock. So what's so awesome about the biochar? Well, there's lots of things that we can do with it in the end. You can restore degraded soil, reclaim polluted soil, neutralize acid soil and wastes, filter water, and also supplement animal feed. And that's just the beginning. There's lots of other details there. And these first 4 benefits here together can help reclaim soil contaminated by mining as well as water contaminated by mining. So all these benefits might sound a little too good to be true. We're going to go into the details where they come from and why there's sometimes trade-offs among them. So to understand these benefits, we need to understand the properties of biochar that they come from. So biochar is porous. It has it's like a sponge, and it has lots of little holes, helps it absorb liquids. It is a sorbent, and stuff sticks to it like a Brita filter. It's a buffer. It helps raise the pH and stabilize it, and it provides habitat for microorganisms. And it is also stable in soil. That's what I was talking about with the climate benefits, that any uncharred organic matter that you add will rapidly decompose, whereas biochar can stay in the soil for hundreds to thousands of years. So these middle properties here, the ability of biochar to act like a filter and to raise and stabilize the pH, are for remediation of mining wastes, what I like to call a 1-2 punch, because these two things combined are really, really effective at removing heavy metals and raising the pH, and they work together. Porosity of biochar also helps too, so I'm just going to call that a sidekick there. Start with the small stuff, the physical properties of biochar. So biochar has a low density, high porosity, as I mentioned. So we're talking about the sidekick here. And what that does is it'll help to restore any degraded soil. So even if a soil has not gotten any heavy metal, contamination, acids, what have you, from a mine, there's a lot of soil that's disturbed during mining. You just a lot of digging happening, and that's not good for the soil. And so adding biochar to soil that's been dug up, like this construction site, just ordinary construction site, not a mine in Iowa, helped dramatically improve the growth of corn, as shown here. This row of corn received char, and the adjacent rows did not. And so just in general, the better the soil is, the less improvement you see with biochar. The worse the soil is, the more improvement you see with biochar. So when it comes to really degraded soils like we would find near a mine, we could stand to see the greatest benefits. So I mentioned biochars are buffers and liming agents. They increase and stabilize pH. And what this is showing is just a naturally acidic soil from Hawaii. And when you increase the amount of biochar added, that increased the growth of trefoil, which is a forage legume. And this same principle helps biochar remediate acid mine soils. So where does biochar get this ability from? Well, it contains what we call alkalis. These are bases, and they will increase pH. They come in various forms. There's some inorganic ones here in blue and green on the bottom. These are probably doing most of the work in the short term. Those who have worked in the mining industry might recognize these compounds as different types of liming agents. So these are known to raise pH, and they can be added separately. They are contained in the biochar. So calcite and dolomite, these first two, are very commonly found in agricultural lime, so ground up limestone, nothing to do with the fruit. This is so we know that these compounds work to raise the pH, and then there's a bunch of other possible ones in there, like calcium oxide, magnesium hydroxide, so those are inorganic. And then the organic stuff is what's directly bonded here to the framework of the biochar, that those honeycomb shapes. In red, there's what we call carboxylate groups that can bond to metals. Calcium is a metal, but it'll work the same with heavy metals. And there's also soluble organic alkalis that help in the short term. And then back to the surface stuff in red, there's some functional groups that are there that can help in soils that are relatively alkaline, but they're unlikely to be contributing that much to pH increases for super acidic soils like we would find near mine sites. And as for which biochars should be used for this, it's been shown that as we increase temperature, we increase the ability of the biochar to neutralize acids. So these are all different biochars. The CS just means corn stover, and we had 3 corn stover biochars in the middle here, and these were increasing in temperature. And as you can see, that dramatically increased the amount of alkalinity as measured as calcium carbonate equivalent. So if you were to add um, uh, powdered limestone, this was about 8% as effective as powdered limestone. That might not sound like much, but it's significant. Um, and then this mixed wood char that's commercially available um, was even more effective, about 11% of calcium carbonate equivalent. And the other factor influencing that would be the amount of salts in the biochar to begin with. So um, specifically calcium, magnesium, sodium, and potassium salts really help present in the initial plant material, really help increase the alkalinity and liming capability of the resulting char. And then down here, this is the effects on actual soil pHs in Iowa. This is not contaminated soil, just FYI. That happened. As for actual contaminated soil, this is an example from Ippolito et al. He's now Jim Ippolito is now at Colorado State University, and he and his colleagues found that you can produce a more powerful effect by combining manure biochar with 1% agricultural lime, again, ground up limestone, and 0.5% poultry litter. The poultry litter just kind of adds nutrients for the plants. And then when they grew that with ryegrass and the contaminated soil, they found the ryegrass did really well because the pH increased quite a bit. So the reason why combining this helps is because the agricultural lime is better at raising the pH more right away, but biochar is better at keeping that pH high in the long term. And so when you combine the two, you raise the pH and keep it there. So that's why the biochar increases pH. Increasing the pH is directly good for the plants, and it's also good for helping to convert the metals into heavy metals into solid form. So the acid mine waste is doubly hazardous because the acids increase the solubility of the metals in addition to the acids having a direct negative effect. And so, raising that pH is really important. And once the pH is raised, biochar's ability to act as a sorbent or filter really, really comes into play because once that pH is raised, these are shown with hydrogens on here, but once the pH is raised, the surface functional groups on the biochar become even more charged. And just like a magnet, opposite charges attract. So we'll look at this first just for nutrients. So these surface functional groups have a partial negative charge to them that becomes a formal charge as you increase the pH, bigger charge as you increase the pH. And then those charges attract the oppositely charged nutrients. And then sometimes they can attract other nutrients too. So this calcium is attracting the phosphate there. So in general, we have an opposites attract situation happening here, but not all of our contaminants have a positive charge. Some have a negative charge. So we have like opposite behaviors happening for the different types of contaminants. So the positively charged contaminants, these are the metals, like the heavy metals, they tend to stick or sorb very strongly to most biochars because most biochars have a bit of a negative charge even when the pH isn't that high. And And you can further increase that as you increase the pH. Then the anions are harder to remove because the biochars tend to have less of the opposite positive charge to attract the those anion contaminants with. So you have to use very high temperature biochars. You have to pyrolyze at about 700 to 900 degrees Celsius to increase the concentration of these positively charged surface functional groups, or we'll get to this, use an iron treatment. So what's happening here is now with heavy metals shown, we have lead, cadmium, copper, zinc, iron, and then arsenic over here, shown as arsenate, is a metalloid. And we have, once again, the negative charges on the surfaces are attracting the oppositely charged metals, and then those metals can potentially in turn attract the metalloids. So how much is being removed? Well, it depends on the metal in question, depends on the biochar in question, depends on the soil in question, but it's anywhere from 50 to 90% being removed. And this also depends if we're talking about tailings or soil or acid mine drainage. This is showing tailings, and that's where the 50 to 90% removal, 97% removal rate is. And for those who enjoy reading graphs, the dark blue is showing before adding biochar, the light blue is showing after adding biochar, and then these are just abbreviations for different biochars down here. And this removal ability does help plants because it's not literally removing stuff from the soil; it's just sticking to the biochar, right? But we know that is reducing the availability to plants. The biochar is holding on to the metals so strongly that the plants can't get them as easily, and we see that by measuring the amount of the heavy metals in plant tissues. So studies have shown that the cadmium and lead are reduced by 30 to 40%, 38 to 39%, and then copper and zinc were reduced by 25% and 17% respectively from these studies. And then that, of course, depends on the amount of biochar you use and the combination with the soil and all that stuff. And this study on the right, once again by Jim Ippolito, is showing that as you increase the amount of biochar, the resistance to copper contamination increases. So with no biochar here, you increase the copper concentration and kill off the vast majority of the plants. But with 0.5% biochar, the plants in the kind of moderate, with soil having a moderate amount of copper, are still pretty resilient, and their resilience improves even more as we increase to 1% biochar. And now we have some survivors at the highest rate of copper at 1 gram per kilogram of soil of copper. That's a lot. And then as we increase to 2% biochar, the gains are not as obvious going from 1 to 2% biochar. So from this, even a small amount of biochar can make a big difference. Now, we said that the properties with the opposite chart, with properties needed to remove cation contaminants like metals versus metalloids and non-metals are opposite from each other because the charges are opposite. And some of these studies that I just referred to actually showed that arsenic was increasing as a result of adding biochar or mixing into soil or mine tailings or acid mine drainage. And so, what do we do about that arsenic? How do we get rid of it? Well, it comes back to what I was alluding to before with iron. So, when it comes to acid mine drainage, a lot of acid mine drainage, which is the liquid waste from mining, um, also has a lot of iron because the acid dissolves iron naturally found in rocks. And once there is enough iron, the iron can work together with the biochar to remove the arsenic. So before reacting with the acid mine drainage, this pine biochar that was made at 450 to 500 degrees Celsius um, had a whole bunch of these oxygen containing surface functional groups. They had a partial negative charge that would normally repel the arsenic, since the arsenic is found as arsenite and arsenate, both with a negative charge. But once you add the iron-rich mine water, the iron bonds to the surface, and then the arsenic bonds to the iron, shown in both of these spots here. And this is, and in the case of this study by Wang et al. Here at University of Arizona, um, this biochar was able to remove over 90% of the arsenic in this way. And that was from the Iron King mine acid drainage. So for those who moved here recently, there was a big spill in like 2015 from the Iron King mine. And so it's important that we treat this water appropriately, and if there is a spill, have treatment options readily available. And this this option is really effective because it forms what's likely a solid mineral that would not readily go back into solution. So it would not become available to plants very easily, to microbes, hopefully not humans, but we haven't tested that yet. And the biochar in this case also increased the pH from 3.2 to 4.0, and pH 4 is where, a lot more microbes can become a lot more happy. It's not as many plants are happy there, but that's why we also add the agricultural lime. Now, what if you don't have that much iron in your waste? Or you're wanting to just filter plain old water that's not from an acid mine, like we have here in Arizona, numerous aquifers that are contaminated with natural arsenic from rocks, because the desert conditions favor a high pH in these aquifers, and that higher pH enables dissolution of arsenic. So it goes into the water easily under these alkaline conditions. And there's not that much iron there. So what if we want to filter that, or some not so iron-rich acid mine drainage? Well, there is a cheaper way to make this iron-loaded biochar. Normally, you have to buy what's called zero-valent iron, or ZVI, which is just the regular iron metal that you see every day, but it's ground up really fine so that you can use it for reacting with stuff. And or you buy iron chloride, also expensive, to mix with the biochar or the feedstock. My former colleague Satnu Bakshi, though, found, sorry, there was an echo. Satnu Bakshi and Sam Rathke found that if you add a very inexpensive mineral, iron-bearing mineral called hematite, to the feedstock, whether that's wood or wheat straw, yard trimmings, what have you, to your feedstock before pyrolysis. So you mix it in before you heat anything up, when it's just room temperature. Mix that, and then pyrolyze at 900 degrees C. You can remove a lot of arsenic, about 14 grams of arsenic per kilogram of biochar added. And the biochar was, of course, not only increasing the pH, but the iron facilitated what's called a redox reaction. So it reacted with the arsenite that was present to make arsenate that was present to make arsenite and iron 3, and then the arsenate bonded to the iron, and the iron bonded to the biochar, so that we had that biochar iron arsenic bridge forming, and it was just really effective. It was so effective that the first couple tests they did, they removed so much arsenic they couldn't even detect it anymore, and they had to redo it multiple times. And then after they reacted the biochar with the arsenic, they used a scanning electron microscope to confirm that the arsenic was actually on the surface, and there it was in green, and this adjacent particle is also showing a lot of iron in red. And so this is a great option for when the waste in question doesn't have enough iron to form the biochar iron arsenic bridge naturally. And then for other anions, in theory, something like this could work too. And if not, just increasing that pyrolysis temperature up high will help remove the other anions. So there's lots of biochars out there, lots of mines, lots of soils at the mines. How do we know when we should use the biochar and which biochar? How do we make these choices? Well, there's trade-offs in benefits, not as many as with just like agricultural soil, but they're there. And therefore, to have the most benefit, we must match biochars with the appropriate mines and soils and contaminants in question. And just to give you an idea of that, this table is showing that we need to identify what most limits the plant growth and look for a biochar with properties that will alleviate that growth limiting problem. So the first bunch of items here are just general desert soil problems. If the soil is too dry, you need a very porous biochar. If the soil is too alkaline, you need an acidic biochar. If it's too saline, you need a not salty biochar. And if it's low in nitrogen, you need a biochar that will hold on to the nitrogen and feed it back to the plants slowly. But now at the bottom here is what we've been talking about with the mine soils. So if acid is the biggest problem, you need a high temperature biochar produced from something salty like manure, or there's lots of plants in Arizona that accumulate salts, and that will produce a biochar with a high alkalinity. And then if metal contamination is the biggest issue, then you want kind of any pyrolysis temperature, although again, having the high temperature will help the metals precipitate. The low temperature, what I was talking about here, is you just get more functional groups on the surface. So there's a trade-off between the pH and the amount of oxygens on the biochar's surface. And then with non-metal and metalloid contamination, we need the high pyrolysis temperature. Wood feedstock seems to work a little better. And then loading with iron helps. So if we put all these things together, like what if you had all three of these problems? Then you probably want to go with the high temperature biochar, since metal removal is pretty good at many pyrolysis temperatures. And having a salty feedstock will help so long as your soil isn't too salty. And iron loading is going to help with the with those non-metal contaminants. So high temperature biochar with some iron added if the non-metal and metalloid contaminants are a concern. So those are found on the right-hand side of the periodic table. So that's the summary there of what to add to which soils, and when some of those are more challenging to make. But with that, thank you all very much. Please let me know if you have any questions. You can email me. You can also find me on social media. It's just at Rivka Fidel. So thanks to all of you, and thanks to everybody who has supported the research presented on these slides.
So hi everyone, I'm Deepika Ghosh. I have a PhD in mine restoration, especially coal mine restoration using biochar. And today I'll be talking about the scope of biochar for degraded mine soil restoration. I am a postdoc with the Northern Arizona University. You are free to contact me if you have any questions. So I'll start. Rebecca already told so much about biochar, so I won't get into the details of what biochar is. I will just like to point to the fact that biochar is gaining a lot of attention. As you can see in my presentation, it was like discussed in a separate panel in the Conference of Parties 27, which happened in Egypt like 2 years back. It appeared around 17 times in the USDA carbon market report to the Congress last year. So like it's like a burning topic to work on right now. So like Rebecca already mentioned, it has a spongy texture. This is the microscopic view of a biochar, and it's like something similar to a sponge. Here you can see the SpongeBob SquarePants. It's just a cartoon. So what can be used for production of biochar? So like if we like differentiate or classify it, so biochar can be produced from any biomass. So during my PhD thesis, I extensively worked in weed biochar because in mining areas, because of the difficult conditions, weeds are a number one problem in mining restoration activities, because oftentimes we need to pull it out of the soil, then leave it to dry, which often causes the problems of mine fire. So I tried using the invasive weed biochar for coal mine restoration and also in chromite mine restoration. Right now, I'm working with the woody biomass, the pine biomass for forest restoration. So I'll talk more about it during my presentation. So how to produce the biochar? I'm sorry. Yeah. So how to produce the biochar? You can see Chris here, like presenting his cool kiln to how to produce biochar. So this is one of the ways you can produce biochar. You can see how it's put on fire, and I think you'll see a live demo today. So this is like a picture of the ones that happened in Flagstaff last year. Another alternative for biochar production is a charboss machine, which we produce biochar with using the slashes we have in Flagstaff. So as you can see, this is the charboss machine where we can put in the biomass, pyrolyze it in an air curtain thing, and then we get the biochar. During my PhD time, these are the common methods I use for biochar production. So as I already mentioned, I used invasive weeds. So you see lantana plant, this is like the number one problem in India. Like it causes havoc, it causes competitive exclusion, it doesn't allow other plants to grow. So taking care of it is a big issue in India. So we tried producing biochar with it with different methods, and we obviously got the biochar. So why are we talking about like why biochar for mine restoration? So as you can see in red, these are the general properties of a mine spoil, of any mine spoil for a matter of fact. It's highly fragmented, it has so low organic content, large pores, or they don't allow permeability or at all. They don't allow water retention. They are totally impoverished and often contain metal contamination. So biochar has the ability to remediate or take care of many of these problems. So let's talk about chromite mine first. So this is a view of a chromite mine, what a chromite mine look like. You see, like everything is gone. These are some of the plantation activities we tried to do, and you can see like everything is gone. So how can we bring back plantation back to these area, or how can we bring biodiversity to this area? So Rebecca already talked so much about how the mechanism, how biochar can restore the heavy metal contamination and help in immobilization it. So it's just I don't want to repeat it. So it's just a layout of how it's done. So if you look into some of my data, so the control here is the mine spoil, the chromite mine spoil, and others are biochar, which has been modified in different ways. So as you can see, the plant available chromite is substantially reduced by biochar application at 2 application rates. So like it's making the highly toxic chromite ions less available to the plant, which is helping its growth. If you see at the the germinated plants, as you can see in control, these are stunted growths, and then as at biochar by applying biochar and modifying the biochar or engineering the biochar, this is just poultry litter that we added, and you can see the changes in plant growth parameters. So yeah, so it's like quite evident that by applying biochar, the metal immobilization is happening, and it's helping promote the plant growth. So let's talk about coal mine spoils. So coal mine spoils are like closer to my heart because that's my PhD work. So I'll talk more about it. This is a typical coal mine spoil. You can see the acid mine lake, the degraded land, like nothing is left. You won't see a single speck of life, no microbial activity, totally impoverished. So what can we do to restore these degraded land? Can biochar be an option? Let's find out. So if we take a series of steps and and make note of what needs to be done, biochar application actually helps a lot. So these are sequential steps that should be considered before biochar application in a coal mine degraded land. So ran a series of experiments where we tried pot experiments, bench scale experiments, and also field trials for 2 years where we looked into how biochar application or invasive weed biochar application helped with the soil properties and plant growth parameters. This is a simple pot experiment that we run, and it is published. So if anyone is interested in looking into the details, you're welcome to. But I would like to point out to the germination and the seed vigor index, which increased like substantially, and the water holding capacity, as you see, was improved significantly. Going to the some bench scale experiments where we looked into the soil enzymatic activities and also the soil respiration. As you can see, compared to the control, uh, compared to the control, the CO2 flux decreased. So in this experiment, we incubated the soil with biochar and left it for 6 months. We didn't take the measurements for the initial six months because we know the initial 6 months it will have more of the labile carbon, which will improve the microbial activity. So to look into how a long-term experiment look into a long-term experiment of how biochar application is affecting the soil respiration, we looked into it. And as you can see, the enzymatic activity for the 6 months period, you can see like it increased at 2% biochar application. Similarly, this has been published, and you're free to read into the details if you're interested. So, getting to the field trial, we applied biochar in a mine spoil, and we studied like various parameters like the soil properties, the enzymatic activities, its carbon sequestration potential, the soil carbon, and all those stuff. And if you can see this graph, like it's recalcitrant carbon, or the carbon that's fixed in the soil by its application, is much more than a reference forest soil. And like it's like a wonderful source of fixing carbon and also improving so many soil properties. And similarly, in the 2 year study, you can see that by applying biochar, the total soil carbon is in an upward trajectory. The inorganic carbon, the labile carbon, of course, and of course, the recalcitrant carbon is like very high compared to like a non biochar added soil. So what's the typical mechanism of how it remediates the soil? You can see it's a series of steps which involves microbes, nutrients, so many chemical changes. Without getting into the depth of it, it's just a cyclic integrated process which promotes soil development, perogenesis, and also promote plant growth. So, if you know about the sustainable development goals, or by which is set up by the UN, and it needs to be addressed by 2030. They have set in 17 sustainable development goals. So, we studied how biochar application in a coal mine spoil can help address these sustainable development goals, and we realized that the sustainable development goal 13 and 15 was like the most evident one, which aims for climate action and life on land. Others were also like influenced by biochar application, but the 13 and 15 were the most evident one. So this is also published material, so if you are interested, you are free to read. So, looking into the limitations and problems of biochar application right now, it's the high cost of production. Because biochar has not been accepted in a large scale yet. So, the production cost is very high, because the techniques that's currently in use is like more sophisticated and costly, I would say. Like, of course, there are methods like Chris proposes the kiln method, but if you look into it, like, because there's not much acceptance yet, the cost, the cycle of demand and supply, the demand and supply is disrupted. So because we don't have much demand, supply is less, and hence the cost is so high. So we are trying to educate people, we are trying to tell to the masses how wonderful it works with our experiments. So hopefully one day they'll accept it, and the cycle of supply and chain will be in motion. Hopeful. So I talked about biochar application in mine restoration in India and in tropical conditions, but there are so many studies in US, and of course Rebecca talked about it too. So it's not like a tropical thing, but it's like a universal thing for now. Like, biochar is really helpful in mine restoration. So right now we are working on mine restoration using I'm sorry, we are using biochar for forest restoration. So this is just a cyclic thing that I showed, like what I'm currently working on. And yeah, special thanks to Chris, my PhD supervisor, Subodh Kumar Maiti, my supervisor in NA, Johan Subhan, and my co-worker, Paul. So yeah, if you have any questions, I am free for any questions.
So I was just wondering if there has been any studies that indicate that the mixture of biochar and calcium carbonate can help the process of the increasing the acidity to help remove the heavy metals from any sort of soil. Just curious.
Yeah, so that was I went kind of fast, but that was the Ippolito et al. Did that. And so that they were the ones who combined them. Let me see if I can still share my screen. So yeah, this is where a manure biochar and ground up limestone were added together, and that enabled ryegrass to grow better. And the pH increased, although it doesn't look like much on this scale. That is a whole pH unit that it increased by. And that's on a log scale. So this was 10 times less acidic.
Are you actively working with any of the mines in Arizona on projects related to this?
Not me personally, but the Trover lab has been working on that. Like with the mine sites. They worked at the mine sites. I'm not sure if they were working with the mine sites, but I would talk to the Trover lab and the Ramirez Andriata lab, because they both have connections to mines. And then also the I'm not sure if they're using biochar on mines, but I know that the Mayer lab here at University of Arizona is working with mine sites.
So we are like working on forest restoration, but our collaborators are actually working on mine restoration, and we are also interested in working in any mine restoration in Arizona, because we currently are not working in Arizona, but some other parts of the US. So yeah.
Would you repeat the name of the labs?
Yeah, so that, I mean, I don't have as many connections with the School of Mining as I would like, but one of them was the Chirover lab. I can actually share my screen for a second, because there's a website that I pulled some of my stuff from. So it's just minerals.arizona.edu/environment/biochar, and that's where the study that I was talking about from the Chirover lab, and I see Rob Roots in the audience. Hi, Rob. That in that lab, they were looking at acid mine drainage from the Iron King Superfund site. And that's the one where the iron in the acid mine drainage formed a bridge between the biochar surface and arsenic. So that was at that site. And then the other labs I mentioned were the Mayer lab, Maier. They have some biochar research and some mine research. I don't remember if it was biochar mine research like combined. And then the third one was the Ramirez Andriata lab. I know they've done studies with thank you for the link. I know they've done studies with mine sites. They have it's called Project Harvest, where they're looking to see like if people live downwind from mine sites, are the soils in their yards contaminated, and does that contamination make its way into the plants? And you can actually kind of browse. It doesn't have literally everything in it right now, but if you go to, I'll just put this in. I guess go to research. You can browse the research in our department at this website. And it's, if you go under like remediation, reclamation, restoration, or pollution dynamics, that should also bring you back around to some of the people I've been talking about. So, and there's some that So Dr. Blankenship, who I also cited in the acknowledgements, does more with like dusty sites, that kind of remediation. Dr. Brousseau examines how chemicals move around. And there's Dr. Trover. This is Dr. Donstova, who does more research with like explosives, contaminants. There's Dr. Mayer, who I referred to, and Dr. Ramirez-Andrada.
Dave, I noticed a question in the Q&A. Can you pull that up?
Is anyone aware of organic disaster debris being processed via biochar methodology?
Are you talking about like solids? I assume like since you said debris, I assume solids, and I presume you mean pyrolyzing that. I have not.
I'm not sure about what organic disaster, like if you can like elaborate. Organic disasters can be like invasive weeds. So I was wondering.
Oh, tree and animal mortality is what the chat says.
Oh yeah, we worked with the tree mortality, the snags that have been affected by wildfire. We actually use that for biochar production. So yeah, we have been working on that.
And a lot of trees felled by storms, like sometimes those are chipped and or sent to like composting sites, or just, they're grouped with yard waste. And so yard waste is well known to be a good thing to make good feedstock to make biochar from. It's just very inconsistent in quality because, one day somebody might trim mesquite, and another day they might trim grass, and another day palm leaves. So still it works. It's just not going to be like, if you're trying to remove contaminants, it's important that you have a consistent product.
Well, appreciate your sharing the presentation and your research. Dipitha, I found it fascinating that you're trying to use invasive plants and you're trying to use something that's already a problem and can put it on there and see if we can make those soils better. So that's really great research that you did. So
thank you so much, Chris.
Cool stuff.